All right, the next topic within this section we're going to talk about is the term-by-term differentiation and integration theorem. So this tells us under what conditions we're able to start with some sort of series, and if we are asked to perhaps differentiate it or perhaps integrate it, how do we handle that situation? In a perfect world, we would like to, if we're asked to integrate a series, it would be nice to, instead of having to find the sum of the series, then integrate it, it would be nice if we could interchange the sigma and the integral symbol. So instead of the integral of the series, we could do the series of the integrals. Because the nice thing is, a power series is just generally adding up a bunch of polynomial terms. It's an infinite degree polynomial. And polynomials are the easiest thing to integrate. So integrating this is very easy, whereas finding the sum of something is a little bit harder than integrating it. All right, so what we're going to have here is a series that converges someplace. So it has some positive radius of convergence. It has a positive radius of convergence. In that case, on that interval, we are able to interchange the order of integration and differentiation. So if we're asked to differentiate this expression, we don't have to first find the sum, then differentiate. We can move the derivative on the inside and take the derivative of this expression, which is right here. Now, you are able to re-index the sum. We won't focus a ton on this. You can just write it like this. Or there is another option here, is even if you don't re-index it, even if you leave this as 0, you still end up getting the same result, just because this n becomes a 0 and the first term goes away anyway. So we can be as technical as we'd like here. Sometimes there is a desire, whether for a technical reason or just for an aesthetic reason, to re-index your sum. But that won't be a major focus here. Same thing for integrating. You can integrate this expression, in which case we get this. And then just like with any integral, when you integrate it, you have an arbitrary constant of integration, which would be this right here. So this is the constant of integration. So these series have the same radius of convergence, but not necessarily the same interval of convergence. So what we mean here is, for instance, let's say we have a series that is centered here at x equals c, and we have a radius of convergence that's positive. So then that means, let's say, here we go, distance of r to x equals c minus r, and over here to x equals c plus r. So what we don't know is the interval of convergence the open interval c minus r to c plus r? Or is it, bracket, bracket? Is it bracket, parentheses? Is it parentheses, bracket? We don't know which one of these four is the actual interval of convergence. All of these four sets, these intervals, they all have the same measure, the same length. Because if you remove or include any one point, any finite number of points, you don't actually change the size of the interval. It's only when you add or remove an infinite amount of points does that change the interval. It has to have some sort of spread. A single point doesn't have a width or a size. It's zero-dimensional. And even if I add 2 points, each one is sort of separated from one another. There's this distance. You can separate them. There's no size there either. It's only when you have a continuum, a whole line of points that are close together. They're dense, so to speak. Okay, so we'll take a look at these last two examples. Example 8, prove that for x between -1 and 1, also note that this is exactly equivalent to the absolute value of x being less than 1. So whether you want to specify it like this or like this, they are equivalent. You're more likely to see this, I believe, at this stage. So prove that this expression has this power series representation. So this is one of these examples in mathematics where you might not think to do this on your own, but once you see it, you'll know to look out for it in the future. So just bear with me for a moment. Notice that if I take the derivative of 1 over 1 minus x, that this is going to be equal to, well, I guess what we could do is write this as 1 minus x to the -1. Then differentiating it would be -1 times the quantity raised to the -2, leave the inside alone, multiply by the derivative of the inside, -1. And this expression right here simplifies to, we have double negative, so it's going to be positive 1 over 1 minus x quantity squared, which is exactly this expression here. Now what's nice about this expression, this is the geometric series that we've been looking at in the past two examples. So this has the representation, the series from n equals 0 to infinity, x to the n. All right, so this series here is equal to 1 over 1 minus x. So now this theorem, the term-by-term differentiation and integration theorem, we're going to be, of course, using the differentiation result from it. If we take the derivative now of each of these sides, this theorem tells us that it is true. So the derivative on this right-hand side, we already know, is 1 over 1 minus x quantity squared. And the derivative on the left-hand side, the term-by-term differentiation theorem says we can take this derivative and we can pass it on the inside. So this would be the series from n equals 0 to infinity of the derivative of x to the n. And we know that the derivative of x to the n is nx to the n minus 1. Now notice here, this is how I mentioned earlier in this video, that the re-indexing of the sum isn't actually truly necessary. You don't have to mess with it if you don't want to, because if you just follow blindly, when you plug in the 0 here, this whole first term goes away. So there's no harm. So if you want to reindex, that's fine, but it doesn't really matter. So what we will do now at this stage is just kind of write out these terms here. So supposedly this 1 over 1 minus x squared is equal to the series of n equals 0 to infinity nx to the n minus 1. So if we write out these terms, we have 0 times x to the -1. See, the term vanishes. Plus, we have 1 times x to the 0 plus 2 x to the 1 plus 3x squared plus 4x cubed, so on and so forth. Rewriting things slightly, we'll have 1 plus 2x plus 3x squared plus 4x cubed plus ... which is exactly this expression up here, with this term just grouped in the ... because I didn't write it all. But there we go. So the step at which this theorem actually enters into our derivation or our proof is from this line to this line. Because if we take the derivative of this series, if this converges absolutely, then we can actually interchange it. So it's the actual swapping of the, or interchanging of the summation and the derivative. That's where the theorem comes into play. Example 9, prove that the arctangent of x is equal to this expression. All right, that's a little strange. So again, like the previous example, we're going to start with something that you might not think to connect, but once you see it, you'll be more likely to seek it out in the future when you encounter problems phrased like this or look like this. So we'll begin with noting. So note that the integral of 1 over 1 plus x squared dx is equal to the arctangent of x plus some constant of integration, c. All right, well, notice that our integrand here, this can be rewritten as 1 over 1 minus negative x squared. Just a double negative trick. The reason for this is we know that a geometric series has the basic format 1 over 1 minus z, where z is just some placeholder, and this is z to the n from n equals 0 to infinity. Oops, sorry, from 0 to infinity. So here in this case, I want this to be a minus sign. Well, if I want this to be a minus, then that means I have to subtract something negative. So then, using the fact that we know that this does converge on the interval -1 to 1, this series should be n equals 0 to infinity negative x squared to the n. This series converges to this expression for x between -1 and 1 exclusively. All right, so now this expression right here, this should hold, so we should be able to replace this 1 over 1 plus x squared, we should be able to replace that with the integral, or excuse me, with the series. So the integral of 1 over 1 plus x squared dx should be equal to the integral of the sum from n equals 0 to infinity negative x squared to the n dx. Now we know that this series converges absolutely for x between -1 and 1. So because of that, the term-by-term integration theorem allows us to interchange the order of the integral and the summation. So this would now become the sum from n equals 0 to infinity the integral of negative x squared to the n dx. Okay? So now, what I'm going to do here before we even, actually I guess we can do this in the same line here. I'm going to rewrite this integrand as -1 to the n times x to the 2n. And then we can just integrate this piece. So this would be negative 1 to the n stays there. It's a constant. Doesn't depend on x. And then integrating x to the 2n would give us x to the 2n plus 1 over 2n plus 1. And of course, we would have our constant of integration, which I'll just call c in this case. The integration theorem here has a capital A. It doesn't matter what you call your constant. So plus c. All right. So notice here that this is an arctangent plus some constant. Well, it is. Technically, that constant would be 0. So in this case, we want to actually see what this constant should be. In this case, we're just going to choose this to be 0. So with c equals 0, this gives us the arctangent of x, which is equal to this series.